In this video, we're going to be talking about Boyle's law, specifically number 4 and 5 in your packet. Boyle's law talks about the relationship between pressure and volume. I want you to think about this relationship for a minute. So if I have a large volume, let's say I have 4 moles of gas, and each of these circles is representing an entire mole of gas. My gas is moving around at a certain temperature, we'll say at room temperature, and it's hitting the walls, it's bouncing off of each other, it's hitting the walls, and so there's a certain pressure exerted. Now if I take the same amount of gas and I put it in a smaller box, so I've decreased my volume, but I still have my 4 gas moles, well then, and it's at the same temperature, so my gas is moving at the exact same speed, so the length of my arrows should be longer, so I want you to notice that my gas is actually hitting the walls harder. There's less space, so when I have a big volume, I might have a little pressure. So let me see, if I have a big volume, I would have a smaller pressure. And if I have a small volume, I would have a bigger pressure. So this is the basic relationship of Boyle's law. If volume increases, and this we are holding temperature constant and the number of moles constant. They're the same for both of these images. So if both of those two things are constant, and I have a large volume, I would have a small pressure. And if I have a small volume, I would have a large pressure. So going to number 4, number 4 states, in a study to see how closely gaseous ammonia, just a reminder, ammonia is NH3. Okay, you can draw that Lewis structure so you can think about how that looks. Obeys Boyle's law. Several volume measurements, here are volume measurements, were made at various pressures, here are various pressures, using 1 mole of ammonia at a temperature of 0 degrees Celsius. So we're holding our moles and our temperature constant. Using the results listed below, calculate Boyle's law constant. So when we're talking about Boyle's law constant, P times V has to equal a constant. So we're going to be calculating that constant for ammonia at various pressures. Calculate the deviation from ideal behavior in each case. Now in this case, with 1 mole at 0 degrees Celsius, our PV, our constant here, so P times V, should be 22.39. And you'll often see this written as 22.4. So that will be what K is, what our Boyle's constant should be. We're looking from the deviation. So if it was ideal, if this gas behaved ideally in an ideal world, not in the real world, this would be P times V. So go ahead and calculate what P times V for each of these actually is. So I've done 3 of these calculations for you, for experiment 1, experiment 3, and experiment 5. And I want you to notice it is never perfect. It's never perfectly 22.39. There's always a slight deviation. So in experiment 1, my deviation is 0.02. The difference between the ideal gas constant and P times V, the ideal Boyle's constant, and P times V in experiment 1 is 0.02. Go ahead and find the deviation, that difference, in each case. So again, I've done this for you for experiment 1, 3, and 5, and I want you to notice what happens to the deviation as pressure is increasing. Well, my deviation is also increasing. 0.23 is a lot bigger than 0.02. So why is my deviation increasing? Well, ideal gases, we don't consider the intermolecular forces between them. So we pretend that there are actually no attractions at all. None of those intermolecular forces exist. But when we squeeze the gas particles together, so when the pressure is higher and the volume is lower, now my gas particles are a lot closer. So the intermolecular forces are coming into existence. So these gas particles, my gas, actually has some sort of attraction between them. And so they don't just fly past each other. They attract each other. They are constantly moving, and they're moving past each other, and they're bumping into walls and bumping into each other, but there is a slight attraction which will actually decrease the volume slightly more than expected, because since there's this attraction, the gas particles tend to be closer. They're attracted to each other, so they're held more together, and they're which causes a decrease in the volume slightly. Now notice, it's not too much of a deviation. 22.16 is pretty close to 22.39, but there is a slight deviation as my pressure increases. So on this graph for exercise 5, we are plotting the values of PV versus P, so our Boyle's constant versus P, for those 6 experiments. And then we are extrapolating, so that means you are extending the line to think what, hypothetically, if we had 0 ATM, if we had no pressure, what would our gas constant be equal to? And I want you to think about this. If pressure was actually 0, this constant would be 0, and we would have no gas. The gas would not have volume, it would not have pressure, it would not be able to exist. So that's why it says hypothetically, what would it be? And then you can compare this graph to the graph on page 3. So go ahead and look at that graph on page 3 and set up your axes just like that graph. And then we need to calculate the value of the y-intercept, which is what this value is. If we have 0 ATM, because 0 is our because ATM pressure is our x-axis, so the y-axis is the point that we will intersect the y. The y-intercept is the point that we will intersect the y-axis. So here I've plotted the 3 points from experiment 1, 3, and 5. And notice I'm plotting PV on the y-axis and pressure on the x. So PV is that Boyle's constant that we calculated in exercise 4. And I can draw, notice it's pretty decent straight line. And now if I extrapolate it to 0 pressure, so I'm going to my y-intercept, extrapolate that, and it would hit right around 22.4. So go ahead and compare that to the graph on page 3.